Tonight, the world is holding still. A house rests quietly beneath the dark sky. Its roof carries the cool weight of the night air. Trees stand in the garden, their branches barely moving. Clouds drift slowly overhead, pale and soft against the darkness. Inside, a cup sits on a table. It does not float toward the ceiling. A book lies close beside it. A lamp waits in the corner. Somewhere, perhaps, a person is asleep beneath a blanket, breathing slowly, held gently against the mattress. Above all of it, the moon hangs in the sky. It does not drift away, and neither do we. This is gravity. It is always here, so constant that it becomes almost invisible to the mind. We notice it when something falls, when a glass slips from a hand, when rain descends from a cloud, when we climb a hill and feel our legs working harder than usual. But most of the time, gravity asks for no attention at all. It simply holds the ordinary world together. The ground beneath your feet is gravity at work. The shape of a falling leaf is gravity at work. The moon's patient path around Earth is gravity at work. The great roundness of planets, the slow turning of galaxies, the stars gathered in distant clusters, all of it is shaped by the same quiet relationship. Every object with mass pulls on every other object with mass. Not only planets, not only stars, everything. You pull very slightly on the chair beneath you. The chair pulls very slightly on you. A mountain pulls on a nearby cloud. A cloud pulls on the mountain. Your body pulls on the moon, though so faintly that the moon has no reason to rearrange its evening plans. Gravity is universal. It never asks whether something is beautiful or ugly, large or small, ancient or newly made. A pebble and a planet both take part. A grain of dust and a distant galaxy both take part. Everything is continually inviting everything else to come a little closer. Imagine the universe as an endless, silent web of invitations. The Earth invites the moon. The moon answers, not by falling straight down, but by curving endlessly around Earth. The sun invites Earth. Earth answers by traveling around the sun, year after year, never quite escaping, never quite falling in. You are invited by Earth too, and Earth is inviting you at this very moment. That invitation is what we call gravity. It is not a rope. It is not a hook. It is not a giant invisible hand reaching down from the sky. Gravity has no sound, no color, no smell, no visible edge. You cannot switch it on. You cannot persuade it to take the afternoon off. Human beings have tried in many ways to escape it. We build ladders, then towers, then balloons, then airplanes, then rockets powerful enough to rise above the air itself. But even astronauts, floating in orbit far above Earth, have not truly escaped gravity. Earth is still pulling them. In fact, gravity is the very reason they remain in orbit. They are falling around Earth, always falling, always missing the ground because they are moving sideways so quickly. It is a strange thought. An astronaut looks weightless. Their hair floats. A pencil drifts through the cabin. A drop of water becomes a trembling sphere. Yet gravity is still there. So what does it really mean to feel weight? This is one of the first small surprises in the story of gravity. You might think weight is gravity itself, but they are not quite the same thing. Gravity pulls you toward Earth. It is the invitation. Your weight is the feeling of being stopped from answering that invitation. Right now, the floor is pushing upward against your feet. Your chair may be pushing upward against your body. Your bed, if you are listening while resting, is pushing upward against your back and shoulders. Earth pulls you downward. The ground refuses to let you pass through it. That gentle but firm resistance is what you feel as weight. If the floor suddenly vanished beneath you, you would fall. And during the fall, for a brief and alarming moment, you would feel weightless. Not because gravity had disappeared. Quite the opposite. You would be following gravity freely. This is why astronauts in orbit float. They and their spacecraft are falling together. Nothing inside the spacecraft is holding them up in the usual way. The walls, the seats, the floor, all fall alongside them. Weightlessness is not the absence of gravity. It is the absence of something stopping you from falling. There is something almost peaceful about that idea, at least when considered from the safety of a warm room. Gravity is not a force that only appears when objects crash downward. It is a constant background presence, a quiet direction written into the world. down. Down is not the same everywhere in the universe. On Earth, down means toward the center of Earth. If you stood on the other side of the planet, your down would point in the opposite direction from someone standing here. Yet neither of you would feel upside down. Both of you would stand with your feet on the ground and your head toward the sky. The Earth is round, and gravity pulls everything inward toward its center. That is part of why large objects in space become round in the first place. Gravity draws matter inward from every direction. Mountains rise and continents shift, but the planet as a whole is shaped into a sphere by its own persistent pull. The moon is round for the same reason. So is the sun. So are many distant worlds we will never visit. Gravity is patient enough to shape planets, patient enough to gather gas into stars, patient enough to pull enormous clouds of matter together until a new sun ignites and begins shining into the dark. Gravity works slowly, but it is never idle. It is always tugging, always gathering, always guiding. For most of human history, gravity seemed too ordinary to be mysterious. Things fell. Rain came down. Stones rolled downhill. The moon moved across the sky. These were simply facts of life. But slowly, people began to wonder. Why does an apple fall toward Earth? Why does the moon not fall in the same way? Why does it keep circling us? Why are tides pulled by the moon? Why do planets travel in their long, graceful paths around the sun? At first, these questions seemed separate. An apple belongs to the garden. The moon belongs to the sky. The ocean belongs to the shore. The planets belong to the heavens. Surely they follow different rules. That was the old instinct. Earthly things were one kind of thing. Celestial things were another. A stone dropped from a hand had nothing to do with the moon moving through the night. Then came a remarkable realization. Perhaps they were all part of the same story. Perhaps the force pulling an apple down is also reaching all the way to the moon. Perhaps the moon is not floating beyond gravity at all. Perhaps it is falling toward Earth continuously, while its sideways motion carries it onward around the planet. This was the great insight that would later be written down with astonishing clarity by Isaac Newton. The same rule governs the falling apple and the orbiting moon. The same quiet relationship holds a sleeping person to Earth and guides worlds through space. It is difficult to overstate how powerful that idea was. The universe stopped being divided into separate kingdoms. The sky was no longer governed by one mysterious set of rules while Earth followed another. The heavens and the ground became part of one connected physical world. A stone falls. The moon circles. The tide rises. A planet turns around the sun. Different scenes. One underlying rule. Newton did not invent gravity. Gravity had been here long before human beings could name it. It was here before cities, before forests, before oceans, before Earth itself had fully formed from dust and fire. What Newton did was something different. He gave humanity a way to describe gravity, a way to calculate it, a way to understand how the pull between objects depends on their mass and their distance apart. He found that gravity is not random. It follows a rule so simple that it can be written in a single equation, yet so deep that it describes the motion of moons, planets, comets, and stars. Later, we will approach that equation slowly. There will be no need to fear it. An equation is only a sentence written in the language of numbers. Newton's equation tells a calm and elegant story. Bigger masses pull more strongly. Greater distance weakens the pull. That is the heart of it. But for now, let us remain with the feeling of gravity before we dissect its language. Feel the quiet steadiness of the room around you. The walls are held to Earth. The floor is held to Earth. The water in the pipes is held to Earth. The air around you is held to Earth, which is why it gathers into an atmosphere rather than drifting away into the darkness. Even the clouds, wandering so freely above us, are not free from gravity. They are lifted and carried by warm air shaped by winds, changed by temperature. But gravity remains beneath all of it, drawing every drop of rain eventually home. There is something humbling in this. We live every moment inside an invisible relationship with the entire planet. Earth pulls you. You pull Earth. Of course, Earth is enormously more massive, so its motion in response to you is too tiny to notice. You do not make the planet wobble beneath your feet. This is probably for the best. Humanity has already given the planet enough administrative difficulties. Still, the pull goes both ways. Gravity is mutual. It is not Earth commanding you downward while you do nothing in return. Every pair of objects pulls on each other. The difference is only in how much each one responds. A child pulls on Earth. A bird pulls on Earth. A falling snowflake pulls on Earth. And Earth answers all of them with its vast, steady presence. This mutual pull extends beyond our planet. The moon pulls on Earth too. We see part of that pull in the tides. The oceans rise and fall in a slow rhythm, responding to the moon's gravity. The water on the side of Earth nearest the moon is pulled a little more strongly. Water on the far side is also drawn into a broad swelling. As Earth turns beneath these ocean bulges, coastlines experience the patient arrival and retreat of tides. The sea breathes to a rhythm partly written by a world in the sky, and the moon itself is held in its orbit by Earth's pull. This is what gravity does best. It makes paths curve. Without gravity, the moon would travel in a straight line, continuing through space without circling us. But Earth keeps inviting it inward. The moon keeps moving sideways. Together, these motions create an orbit. A circle, or more precisely, a gentle oval. Not a track carved into space. Not a rail. An orbit is a dance created by falling and moving forward at the same time. Earth performs the same dance around the sun. The sun performs its own larger motion within the Milky Way. The Milky Way moves among other galaxies. Nothing is truly still. Yet gravity gives movement its shape. It bends straight paths into arcs. It gathers scattered dust into worlds. It turns chaos into systems. It creates structure without ever making a sound. So tonight, when you look at the moon, or simply imagine it beyond the ceiling and clouds, remember that it is not hanging in the sky by magic. It is traveling, falling, turning, answering Earth's silent invitation. And you are answering it too. Your body rests because Earth pulls it close. The cup remains on the table because Earth pulls it close. The trees sink their roots into the soil because Earth pulls them close. The clouds drift overhead. The rain waits within them. The moon circles above. And the whole familiar world remains gathered together by an invisible rule that reaches from your quiet room to the edge of the cosmos. Gravity is not loud. It does not announce itself. It does not need to. It is the quiet keeper of connection. And in the next chapter, we will meet the person who first showed that this hidden connection could be understood, measured, and written into one of the most influential equations ever discovered. Before Newton gave gravity a universal language, people had been watching things fall for thousands of years. They watched rain return from clouds to rivers and fields. They watched stones slip from hands. They watched fruit drop from branches. They watched dust settle after a wind. And, like every good observer of nature, they asked a simple question. Why down? Why does a stone fall toward Earth instead of rising into the sky? Why does water run downhill? Why do we remain on the ground even while the world turns beneath the sun? For much of human history, the answer seemed obvious. Heavy things belong below. Light things belong above. Smoke rises. Fire reaches upward. Stones descend. Soil stays near the ground. Water flows toward the lowest place it can find. The world appeared to have a natural order, and everything seemed to be quietly searching for its proper place. This was the view associated with Aristotle, one of the most influential thinkers of the ancient world. Aristotle imagined that Earth sat at the natural center of the universe. Heavy materials, he believed, moved downward because they were trying to return to their natural home. Earth and stone belonged at the center. Water belonged above Earth. Air belonged above water. Fire, being light and restless, belonged higher still. It was an elegant picture. A stone falls because it wants to be where stone belongs. A flame rises because fire wants to be where fire belongs. For a very long time, this explanation felt satisfying. It matched ordinary experience. It gave each thing a place. It made the universe feel arranged, layered, almost architectural. And yet, there was a problem hiding inside it. A problem that only becomes visible when someone begins asking more careful questions. Aristotle believed that heavier objects should fall faster than lighter ones. This also sounds perfectly reasonable at first. Drop a large rock and a small pebble. Surely the large rock reaches the ground first. It is heavier. It seems more determined. It seems to have more of whatever makes things fall. If you drop a feather beside a stone, the stone hits the ground while the feather drifts and twists in the air. So the conclusion appears obvious. Heavy objects fall quickly. Light objects fall slowly. Case closed. Human beings are very good at treating the first thing they see as the final thing they need to know. It saves time. It also explains a surprising amount of history. But the falling feather was not revealing a simple truth about mass. It was revealing something else. Error. The feather does not fall slowly because Earth is less interested in it. Earth pulls on the feather just as faithfully as it pulls on the stone. The difference is that air pushes against the feather much more strongly relative to its weight. The feather has a broad, delicate shape. It catches the air. It flutters. It is constantly slowed by invisible collisions with countless molecules in the atmosphere. The stone is also pushed by air. It simply does not care very much. It is compact, dense, heavy for its size. The air presses against it, but the stone continues down with such confidence that the resistance barely changes the story. This distinction would become one of the great lessons of early science. Nature often looks more complicated than it really is because several effects are happening at once. To understand what is fundamental, you have to find a way to separate them. This is where Galileo Galilei enters the story. Galileo lived in Italy in the late 16th and early 17th centuries. He was not the first person to question old ideas, but he had a rare gift for turning simple questions into experiments. He looked at motion not as something to explain with tradition or intuition, but as something to observe carefully. He asked what would happen if we removed the confusing details. What if we could ignore the air? What if we could make objects roll slowly enough to measure? What if the heavy stone and the light stone were not following different laws at all? A famous story says Galileo climbed the Leaning Tower of Pisa and dropped objects of different masses from the top. The story is difficult to confirm exactly as it is usually told, but it captures the spirit of his work. Galileo challenged the assumption that heavier objects must fall much faster. His observations led toward a surprising conclusion. Without air resistance, objects fall together. A heavy cannonball and a light stone accelerate downward in the same way. Not almost the same way. The same way. This is one of those facts that sounds simple once you hear it. But it asks the mind to give up an old instinct. The heavy object feels as though it should fall faster. It looks more forceful, more serious, more committed to the task. But gravity does not play favorites in that way. Earth pulls more strongly on a heavier object, yes, but the heavier object also has more inertia. It is harder to accelerate by exactly the same proportion. These two facts balance each other. The result is quiet and universal. In the absence of air, everything falls alike. A pebble, a brick, a hammer, a human being, a drop of water, a grain of sand. This was demonstrated dramatically many centuries after Galileo, on the moon. In the moon's near vacuum, an astronaut dropped a hammer and a feather at the same time. With no meaningful air to slow the feather, both fell together and reached the lunar ground at the same moment. The feather did not suddenly become heavy. The hammer did not become less heavy. They were simply answering the same call. Imagine a perfectly still elevator. Its walls are sealed. The air has been removed. Inside are a large book and a small stone. You hold them side by side. Then you let go. There is no air to catch the stone. No air to slow the book. No invisible cushion pressing against either object. For a moment, both begin to fall. Not because the book is more important. Not because the stone is denser. Not because one has earned a faster trip downward. They fall together because Earth is inviting both of them inward, toward its center, according to the same quiet rule. The large book and the small stone are not following separate laws. They are participants in one shared relationship. This idea seems almost obvious now, but it was not obvious then. It changed the character of science. Before Galileo, people often explained motion by asking what kind of object something was. A stone is heavy. A flame is light. A feather is delicate. Each thing appeared to possess its own natural behavior. Galileo began to show that motion could be governed by simpler principles beneath those appearances. The world did not need one rule for stones, another for books, another for cannonballs, and another for falling fruit. Perhaps there was one rule underneath them all. This was a profound shift. It meant that nature might be simpler than it first appears. It meant the job of science was not merely to collect familiar stories about the world. It was to test them, to isolate one effect from another, to notice where the obvious answer might be hiding a deeper truth. Galileo also discovered something else important. Falling is not simply motion downward at one steady speed. An object falling freely speeds up as it goes. At first, it moves slowly, then faster still. Gravity does not merely tell an object to go down. It continually changes its motion, adding speed with every passing moment. This is why a fall from a great height becomes dangerous. The longer an object falls, the faster it travels. Gravity has had more time to do its quiet work. Again, air can make this story seem confusing. A falling leaf may drift at a nearly steady pace because air resistance quickly balances gravity's pull. A skydiver eventually reaches a speed where the air pushes upward strongly enough to balance the pull downward. At that point, they no longer accelerate much, but remove the air, and a simpler rule emerges. The falling object keeps speeding up. This is what makes the moon so interesting. The moon is not resting in the sky. It is falling. That sentence may sound wrong at first. The moon has been up there for billions of years. Falling things are supposed to come down. They are supposed to strike the ground. The moon has done neither. But Galileo's work opened the door to a new way of seeing the problem. What if falling does not always end in a collision? What if something could be falling toward Earth while moving sideways so quickly that Earth curves away beneath it? Imagine standing on a very high mountain and throwing a stone outward. It travels forward, then gravity pulls it down, and it strikes the ground. Throw it faster, and it travels farther before it lands. Throw it faster still, and it travels farther again. Now imagine a throw so powerful that as the stone falls, the curved surface of Earth falls away beneath it at exactly the same rate. The stone keeps falling, but it never reaches the ground. It circles the planet. That is an orbit, and that is the bridge between Galileo's falling objects and Newton's universal gravity. A falling apple and the orbiting moon are not opposite kinds of events. They are close relatives. One falls straight enough to reach the ground. The other falls sideways fast enough to keep missing it. Before Newton, this connection had not yet been expressed with the full clarity it deserved. Galileo had transformed the study of motion. He showed that falling objects obey simple patterns. He weakened the old belief that heavier things naturally fall faster, simply because they are heavier. There was still a great question waiting in the quiet. What reaches from Earth to the moon? What pulls the moon inward from so far away? Why does the pull grow weaker with distance? Why does it shape one object's fall in a garden and another object's path in the heavens? The old universe separated Earth from the sky. Galileo began to soften that boundary. Newton would remove it, and once he did, falling objects, ocean tides, wandering planets, and the moon's endless curve through the night would all become parts of one elegant, invisible conversation. In the 17th century, England was changing. Sailing ships crossed oceans with maps that were still incomplete. Clocks were becoming more precise. Telescopes were revealing new details in the night sky. People were beginning to believe that nature, however mysterious it seemed, might obey rules that the human mind could discover. The world was full of motion. Ships moved over dark water. Cannons sent iron balls through the air. Pendulums swung in tall clocks. Apples fell from trees. And above it all, the moon traveled through the sky with steady, patient certainty. Into this world came Isaac Newton. Newton was not yet the white-haired figure from paintings. He was young, intensely curious, private, and capable of spending long periods thinking about a single question while the rest of the world carried on with the useful business of growing food, trading goods, and avoiding unnecessary thought. He lived during a time when old ideas were being tested. Galileo had shown that falling objects did not behave as Aristotle had imagined. Johannes Kepler had discovered that planets move around the sun in graceful, predictable paths. Telescopes had made the heavens feel less like a perfect, unreachable realm and more like a real physical place. The sky was beginning to look earthly, and Earth was beginning to look cosmic. Then came the years of plague. In 1665, disease spread through England, and Cambridge University closed its doors. Newton, then a student, returned to the countryside, to his family home in Woolsthorpe. There, away from lectures and crowded rooms, he spent time thinking. The famous story says an apple fell from a tree and struck Newton on the head, instantly causing him to invent gravity. It is a good story. It has survived because it is simple, visual, and because humanity has always enjoyed the idea that a great scientific revolution might begin with a piece of fruit behaving badly. But the real story is quieter. There is no reliable reason to believe an apple hit Newton on the head. Newton himself did later describe seeing apples fall and wondering about them. The apple may have been an inspiration, a small ordinary event that opened the door to a very large question. Not, why do apples fall? Everyone already knew apples fell. Newton's question was more ambitious. Why does an apple fall straight toward Earth? And if Earth can pull an apple downward, how far does that pull reach? Does it stop at the top of the tree? Does it stop above the clouds? Does it fade somewhere beyond the air? Or does it continue outward, reaching all the way to the moon? This was the extraordinary question. If an apple falls toward Earth, could the moon also be falling? At first, this seems impossible. The apple falls down. The moon stays up. The apple strikes the ground in seconds. The moon has traveled around Earth for longer than any human history can remember. How could these be versions of the same event? But Newton had inherited a crucial idea from Galileo. Falling does not mean moving only straight downward. Falling means being continuously pulled toward Earth. What happens next depends on how much sideways motion an object also has. Imagine standing on the peak of an impossibly high mountain. The air is clear. The horizon curves faintly in the distance. In your hands is a ball. You throw it gently. It moves forward for a short distance. Gravity begins pulling it downward immediately. Its path curves toward the ground, and it lands nearby. Now throw it harder. The ball travels farther before gravity brings it down. It still falls. It curves downward, but it lands farther away. Throw it harder still. The ball crosses a greater distance. The ground is farther away when it finally reaches it, because Earth curves beneath its path. Now, keep increasing the speed. The ball travels farther, then farther still. And eventually, in this thought experiment, it reaches a remarkable speed. It falls toward Earth continuously, but Earth's curved surface falls away beneath it at exactly the same rate. The ball keeps moving forward. Gravity keeps pulling it inward, but it never reaches the ground. It falls forever. That is an orbit. An orbit is not a path where gravity has stopped working. It is a path created because gravity is working continuously. The moon is not hanging above Earth. It is not balanced on an invisible shelf. It is not being held in place by an ancient celestial mechanism that requires maintenance on alternate Thursdays. The moon is falling. Always falling, but it has enormous sideways motion. As it moves forward through space, Earth's gravity pulls it inward. Its path curves, yet the surface of Earth curves away beneath it. So the moon keeps missing Earth. Again, and again, and again. For billions of years, the moon is like Newton's imagined cannonball, thrown with exactly the right sideways speed. Not fast enough to escape Earth entirely. Not slow enough to fall directly into it. It is held in a perpetual curve, a never-ending fall around the world. This is one of the most beautiful ideas in science because it joins two scenes that seem completely different. An apple dropping in a garden, a moon circling in the sky. One is close, one is distant. One lasts a moment, one lasts a month. But both are responding to the same pull. Earth reaches out to the apple. Earth reaches out to the moon. The difference is not the rule. The difference is the motion. Think of the apple again. When it separates from the branch, it has very little sideways speed. Gravity pulls it down and it reaches the ground almost directly beneath the tree. The moon is different. It is already racing sideways through space. Gravity bends that motion inward, but it does not stop it. The moon keeps moving forward while falling toward Earth. That combination creates its orbit. Sideways motion carries it onward. Gravity curves its path. Neither action wins, neither action disappears. Together, they make a circle-like journey around the planet. More precisely, the moon travels in a gentle oval rather than a perfect circle. Its distance changes slightly over time. Its speed changes slightly too, but the central picture remains true. The moon is in continuous free fall around Earth, and Earth is not completely still in this relationship either. The moon pulls on Earth. Earth pulls on the moon. They move around a shared center of balance, though that center lies deep within Earth because Earth is so much more massive. Gravity is always mutual. The larger object usually moves less, but it is never entirely uninvolved. This matters because Newton was not searching for a one-way force. He was uncovering a universal relationship. Every mass pulls on every other mass. Earth pulls the apple pulls Earth. Earth pulls the moon pulls Earth. The sun pulls Earth. Earth pulls the sun. The pulls are not always equally noticeable. Earth responds only imperceptibly to an apple. The sun responds only slightly to Earth. But the relationship is there, everywhere. This is what made Newton's thought so revolutionary. Earlier thinkers had often treated the heavens and Earth as separate worlds. On Earth, objects fell, rolled, broke, and decayed. In the heavens, planets and stars moved with calm perfection, governed by different principles. Newton saw something more unified. The same nature that made a stone fall could guide the moon. The same law that shaped a cannonball's arc could hold planets in orbit. The universe was not divided into ordinary Earth below and mysterious heavens above. It was one connected system, one set of rules, one quiet pull reaching through space. It is worth pausing here, because this idea transforms the night sky. When you look at the moon, you are not looking at a distant lamp attached to the darkness. You are looking at a world in motion, a world falling around us, a world traveling sideways at tremendous speed while being gently, constantly drawn inward by Earth. The moon appears calm because it is far away, but it is always moving, always curving, always missing us, and Earth is doing something similar around the sun. Earth moves forward through space at enormous speed. The sun pulls it inward. Earth falls toward the sun, but it also moves sideways so swiftly that it keeps missing the sun. That is why a year exists. A year is Earth completing one long fall around the sun. The same pattern repeats across the solar system. Mercury falls around the sun. Venus falls around the sun. Mars falls around the sun. Jupiter, immense and distant, falls around the sun. Moons fall around planets. Comets sweep inward and outward, following long stretched paths through the darkness. Gravity shapes all of them, not with visible ropes, not with engines, not with forceful commands, with a steady invitation. Come a little closer, move a little differently, curve, return, continue. Newton's great achievement was not simply noticing that an apple fell. It was daring to imagine that the apple and the moon belonged to the same story. It required a leap of thought. The moon was unimaginably far away by the standards of his time. Nobody could travel there. Nobody could touch its surface. Yet Newton understood that distance did not place it beyond the reach of natural law. Gravity could extend outward. It could weaken with distance, but it did not simply stop. This immediately raised a new question. If gravity reaches the moon, how does its strength change as the distance grows? Earth's pull is strong near the ground. We feel its effects every moment. But the moon is roughly 250,000 miles away. Why is it not pulled down as quickly as an apple? Newton suspected that gravity became weaker with distance in a precise way. Not randomly, not approximately, according to a simple rule. To test this, he compared the fall of objects near Earth with the moon's curved path around the planet. He asked whether the same gravitational pull, weakened by distance, could account for both. It could. This was the beginning of universal gravitation. The word universal matters. It means the rule applies everywhere, not only in gardens, not only in England, not only on Earth. Every object with mass participates. A drop of rain, a mountain, a planet, a star, a galaxy. Even two people standing quietly in the same room pull very slightly on each other. The pull is far too small to feel, and thankfully does not compel anyone to walk slowly across the room in a dramatic cosmic reunion. But it is real. Gravity reaches between all things. Sometimes its invitation is barely a whisper. Sometimes, as with planets and stars, it becomes the architect of entire worlds. Newton had found the bridge. The apple was not merely falling. The moon was not merely orbiting. Both were following gravity. And soon Newton would express that idea in a compact equation, a small arrangement of symbols carrying a vast message. Mass matters. Distance matters. And every object in the universe is connected to every other by a quiet pull that never entirely disappears. There is a moment in every great story of discovery when a huge idea becomes small enough to fit on a page. For Newton, that moment was an equation, a short line of symbols. Quiet, compact, almost modest. And yet this small equation describes the fall of an apple, the path of the moon, the pull of tides, the motion of planets, and the slow gathering of stars into galaxies. It says that every object with mass pulls on every other object with mass. It says that the strength of that pull depends on two simple things: how much mass the objects have, and how far apart they are. That is all. No special rule for apples. No separate rule for moons. No private rule for planets. One rule. One relationship. One equation that connected everything. Let us say it slowly. The gravitational force between two objects equals a tiny constant from nature, multiplied by the mass of the first object, multiplied by the mass of the second object, divided by the square of the distance between their centers. It may sound long when spoken this way, but it contains only four ideas: the force, the first mass, the second mass, and the distance, plus one tiny number that nature keeps quietly in the background. We can take them one at a time. First, there is the force. Newton used the letter F for force. In this equation, F means gravitational force. It means the strength of the mutual pull between two objects. Earth pulls on you. You pull on Earth. The pull is shared. It is always shared. But Earth has so much mass that its response to you is too small to notice. You do not make the planet rise slightly to meet your feet each morning. This may be fortunate. It would make getting out of bed even more emotionally complicated. Still, the pull goes both ways. If you and another person stand across a room from one another, you are pulling on each other. Very gently, so gently that no instrument in ordinary life would ever notice it. But the force exists. The same rule applies to a pebble and Earth, to Earth and the moon, to the moon and the sun, to the sun and every planet moving around it. Gravity does not choose important objects. It does not reserve itself for large things. It is simply more noticeable when at least one object is very massive. Next come the two masses. Newton called them the mass of the first object and the mass of the second object. Mass is not quite the same as weight. Weight is what you feel when gravity pulls you and the ground pushes back. Mass is more fundamental. Mass tells us how much matter an object contains and how strongly it resists changes in motion. A bowling ball has more mass than a tennis ball. Earth has more mass than a mountain. The sun has far more mass than Earth. And a galaxy contains more mass than we can comfortably imagine. In Newton's equation, mass strengthens gravity. Give one object more mass, and the pull becomes stronger. Give both objects more mass, and the pull becomes stronger still. Double the mass of one object, and the gravitational pull doubles. Double the mass of both objects, and the pull becomes 4 times as strong. This is why the sun has such authority over the solar system. The sun is not merely large. It contains almost all the mass in the solar system. Its gravitational pull reaches outward across enormous distances, guiding the paths of planets, comets, dust, and distant icy worlds. Earth orbits the sun because the sun is so massive. The moon orbits Earth because Earth is much more massive than the moon. And you remain near the surface of Earth because Earth is unimaginably more massive than you. Mass strengthens the invitation. A small object whispers. A large object speaks more firmly. A star speaks across millions of miles. A black hole, where immense mass is packed into a tiny region, speaks with an intensity that can bend light itself. But even the strongest gravitational message has another condition: distance. Newton used the letter R for distance. More specifically, it means the distance between the centers of the two objects. For small things, this is easy to imagine. If you hold 2 marbles, you would measure from the center of one marble to the center of the other. For Earth and the moon, we measure from Earth's center to the moon's center. For Earth and the sun, we measure from the center of Earth to the center of the sun. This detail matters because gravity does not begin at the surface of a planet and stop at the surface of another. The whole mass of each object participates in the relationship. Now comes the most important and surprising part of Newton's equation. Distance is not merely divided once, it is divided by its square. The square of distance. This means gravity weakens very quickly as objects move apart. If you double the distance between two objects, gravity does not become half as strong. It becomes 4 times weaker. If you make the distance 3 times greater, gravity becomes 9 times weaker. If you make the distance 10 times greater, gravity becomes 100 times weaker. This is called the inverse square law. The name sounds stern, but the idea is gentle. Distance makes gravity fade, and it fades faster than most people expect. Imagine 2 lanterns in a dark field. One lantern is on one side of the field. The other is far away. A brighter lantern sends out more light. That is like a larger mass creating a stronger gravitational pull. But as the light spreads outward, it becomes thinner. Less of it reaches any particular place. Move farther away, and the glow weakens quickly. Gravity behaves in a similar way. Mass strengthens the message. Distance makes it fade. A massive planet creates a powerful pull near its surface, but far away, that same pull is spread across an ever larger region of space. It is still present. It never vanishes completely, but it becomes weaker and weaker. This explains why you feel Earth's gravity so clearly, while the gravitational pull of distant stars does not tug you across the room. The stars are immensely massive, but they are also unimaginably far away. Distance is doing a great deal of quiet work. It also explains why gravity holds the moon in orbit without simply pulling it down to Earth. Earth's gravity reaches the moon, certainly, but at the moon's great distance, the pull is weaker than it is near Earth's surface. The moon is also moving sideways at tremendous speed, so Earth bends its path inward rather than pulling it directly down. The moon falls. The moon moves sideways, and distance helps set the delicate balance between those two motions. Now there is one final part of Newton's equation. The letter Gg is called the gravitational constant. It is a tiny number, an extraordinarily tiny number. It tells us something important about the universe. Gravity is universal, but compared with the other forces of nature, it is remarkably weak. You can feel this without knowing any mathematics. Lift a book from a table. Earth, with all its vast mass, is pulling that book downward. And yet your hand can lift it upward with little effort. A small magnet can lift a paperclip against the pull of the entire planet. An ordinary chair can hold your body up. The floor can stop you from continuing downward. Gravity is powerful when huge masses gather together, or when vast distances and immense times are involved. It shapes planets and stars. It organizes galaxies. It can compress matter so intensely that even light cannot escape. But on the scale of everyday objects, gravity is gentle, patient, almost shy. That is why Newton needed G in his equation. G is nature's conversion number. It tells the equation exactly how much gravitational pull comes from a particular amount of mass at a particular distance. Without G, the equation would have the right shape but the wrong scale. It would know that larger masses should pull more strongly. It would know that larger distances should weaken the pull. But it would not know precisely how strong gravity should be in our universe. G supplies that final instruction. It is the small, quiet number that makes Newton's rule fit reality. So let us return to the full equation, but without fear. The gravitational force between two objects equals G, multiplied by the first mass, multiplied by the second mass, divided by the square of the distance between them. That is Newton's law of universal gravitation, and beneath its symbols is an almost comforting message. More mass means more pull. More distance means much less pull. Everything else is detail. A mountain pulls more strongly than a pebble. Earth pulls more strongly than a mountain. The sun pulls more strongly than Earth. But move far enough away from any object, even a massive one, and its gravity grows faint. It remains, but it fades. This is why the universe can be both connected and spacious. Everything pulls on everything else. Yet distant things are allowed room to move. The moon feels Earth's pull, but not so strongly that it crashes down. Earth feels the sun's pull, but not so strongly that it falls directly into the sun. Planets move in paths shaped by the balance between gravity and motion. Stars gather in galaxies, yet galaxies remain vast enough for light to travel between stars for years, centuries, or far longer. Newton's equation is not only a rule for falling objects, it is a map of relationships. It tells us that the universe is not a collection of isolated things sitting in empty space. Every object is connected, however faintly, to every other. Connection may be too small to notice. A cup pulls on a book. The book pulls on the table pulls on the house pulls on the moon pulls on the sea pulls on the shore. All of these pulls are real. Most are too weak to matter in daily life. But gravity does not need to be dramatic to be real. It is often most powerful when it has time. A tiny gravitational pull, acting over millions of years, can shape a world. It can gather scattered dust into a planet. It can pull gas together until a star ignites. It can guide moons into stable paths. It can slowly change an orbit, raise tides, stretch worlds, and arrange entire galaxies into vast rotating forms. The equation contains all of this possibility. A few letters, a few relationships, a universe of consequences. And there is a deeper beauty in the way Newton found this rule. He did not need to visit the moon. He did not need to touch a planet. He did not need to travel beyond Earth's atmosphere. By observing falling objects, studying motion, and thinking carefully about distance, he found a pattern that reached into the sky. He showed that the moon was not beyond understanding simply because it was distant. He showed that the heavens were not governed by a separate kind of reality. The same law that guides a falling stone also guides a world. The same equation that describes a small pull between ordinary objects also describes the immense pull between stars. That is what makes it universal. It does not change its mind at the edge of the atmosphere. It does not become a different law beyond the clouds. It reaches outward, quietly, faithfully, without needing to be seen. So if the symbols ever felt intimidating, let them become simple again. F is the pull. The two masses are the things doing the pulling. The distance tells us how much the pull fades across space. And G is the tiny natural number that sets gravity's strength in this particular universe. Force. Distance. A quiet law. The next time you see the moon, you can imagine this equation working invisibly between Earth and that bright distant world. Earth's mass, the moon's mass star, the immense distance between them, and the gentle gravitational force that binds their endless dance together. Nothing visible connects them. No rope, no rail, no hand, only a relationship written into nature itself. A relationship that Newton learned to describe, and a relationship that, even now, is holding the universe in motion. Distance is the quiet trick inside gravity. Mass is easy to understand. More mass means more pull. A larger planet pulls more strongly than a smaller one. A star pulls more strongly than a planet. A galaxy pulls more strongly than a single star. That part feels natural. But distance is where gravity becomes surprising. Because gravity does not fade gently. It fades quickly, much more quickly than our intuition expects. Newton's equation contains this idea in one small detail. The distance between two objects is squared, not simply counted once. Squared, and that changes everything. It means that if you move twice as far away from an object, its gravity does not become half as strong. It becomes 1/4 as strong. Move 3 times farther away, and gravity becomes 1/9 as strong. Move 10 times farther away, and the pull becomes 100 times weaker. Distance is not a small adjustment. Distance is an amplifier of emptiness. This is called the inverse square law. The name may sound like something designed to make a room fall silent during a school lesson, but the idea itself is simple. As you move away, gravity spreads out, and as it spreads, less of its influence reaches any one particular place. Imagine standing in an enormous circular room. The room is perfectly quiet. You stand in the center and whisper a single word. Close to you, the whisper is clear. A person standing nearby can hear it easily. But farther away, the sound has spread outward. It has more space to fill. It reaches a wider circle of listeners. The same small amount of sound must now cover a much larger area. So the whisper grows faint, not because the whisper has chosen to stop, not because the room has become unfriendly, but because the sound is being shared across more and more space. Gravity behaves in a similar way. A planet's gravitational influence reaches outward in every direction. Near the planet, that influence is concentrated. Farther away, it is spread across a much larger region of space. The pole remains. It does not suddenly end at a border. There is no sign floating above Earth's atmosphere that says, "Gravity stops here. Thank you for visiting." Instead, the pole becomes weaker gradually, then weaker still. And because distance is squared, it weakens rapidly. This is why Earth feels so powerful beneath your feet. You are close to it. Very close. Even if you are standing on a mountain, even if you are flying in an airplane, even if you are in a spacecraft hundreds of miles above the surface, you remain close to Earth compared with the enormous scale of space. Earth is large. It's centralized thousands of kilometers below your feet. But in cosmic terms, you are almost touching it. That is why Earth's pull dominates your daily life. It holds the atmosphere near the planet. It brings rain down from clouds. It guides rivers downhill. It keeps oceans gathered around a world rather than scattered into the blackness of space. It holds you close. Now compare Earth with the Sun. The Sun has vastly more mass than Earth. Its gravitational pull is immense. It reaches throughout the solar system, guiding the paths of planets, moons, comets, asteroids, and distant fields of ice and rock. And yet, when you drop a cup in your kitchen, the cup falls toward Earth, not toward the Sun. Why? Because Earth is close. The Sun is tremendously far away. The Sun's pull reaches you, certainly. It is part of the reason Earth travels in its long path around the Sun. But Earth is near enough that its local gravity is much stronger for objects close to its surface. This is one of gravity's great balancing acts. The Sun governs the large journey. Earth governs the local one. The Sun holds Earth in orbit. Earth holds the Moon in orbit. Earth holds your coffee cup on the table, and the cup in its own tiny way pulls back on Earth. Everything is connected. But distance decides which connection matters most at a particular moment. Imagine you are standing beside a large bonfire on a cool night. The fire is bright and warm. A few steps away, its heat reaches you strongly. Walk farther away, and the warmth fades. Walk farther still, and you can see the flames but no longer feel them. The fire has not become smaller. It has not stopped giving off heat. You have simply moved into a wider region where that energy is more thinly spread. Light does this. Sound does this. Gravity has a similar pattern. The farther you go, the more space lies between you and the source of the pull, and the more rapidly its influence fades. This helps explain the architecture of the solar system. Near the Sun, gravity is strong. The inner planets move quickly in their orbits. Mercury, closest to the Sun, races around it in a short year. Venus moves a little farther out. Earth takes 1 year. Mars, farther away, takes longer. Then come the giant planets, traveling along vast paths where the Sun's pull is weaker, but still strong enough to guide them. Jupiter takes nearly 12 Earth years to circle the Sun. Saturn takes almost 30. Neptune, far out in the cold darkness, takes more than a century and a half. The Sun's gravity reaches all of them. But distance changes the rhythm of every orbit. Closer worlds move faster. Distant worlds move more slowly. Gravity is still the same rule, but its strength is different at different distances. Now let us return to Earth, because distance also clears up one of the most persistent misunderstandings about astronauts. Astronauts in orbit are not beyond gravity. They are not floating because Earth has lost interest in them. They are floating because they are falling continuously. A spacecraft orbiting Earth may be only a few hundred kilometers above the surface. That sounds high when you imagine climbing there, but compared with Earth's size, it is a thin layer above the planet. Earth's gravity is still very strong there. An astronaut aboard a space station feels almost all of Earth's familiar pull. The station, the astronaut, the tools, the food packets, the water droplets, all of them are being pulled toward Earth together. But they are also moving sideways at tremendous speed, so they fall around Earth rather than straight down into it. The space station keeps missing the ground. Every moment, it is pulled inward. Every moment, its sideways speed carries it forward. And every moment, Earth curves away beneath it. This creates orbit. The astronauts float not because gravity has disappeared, but because nothing beneath their feet is pushing upward against them. Remember the difference between gravity and weight. Gravity is the pull. Weight is the feeling of being stopped from falling. On Earth, the floor stops you. In orbit, The spacecraft and the astronaut fall together. There is no ordinary floor holding the astronaut up, so they float. It is not freedom from gravity, it is surrender to gravity. A careful, controlled, endlessly curving fall. This is why the phrase zero gravity is not quite right for astronauts orbiting Earth. It is useful shorthand. But the real story is more beautiful. Gravity is present. Gravity is doing nearly all the work. Without Earth's gravity, the space station would not orbit. It would continue in a straight line, leaving Earth behind. Orbit is not where gravity ends. Orbit is where gravity becomes a path. And distance is what makes that path possible. Close enough to Earth, gravity bends the station's motion sharply. Farther away, the pull is weaker. An orbit can still exist, but it changes. The object moves more slowly and takes longer to circle Earth. The moon is much farther away than the space station. Earth's pull on the moon is weaker, but the moon is also moving in a carefully balanced way, falling toward Earth while traveling sideways around it. Distance does not destroy the relationship. It changes its shape. It changes its speed. It changes its rhythm. This is true everywhere in the universe. Consider the tides. The moon pulls on Earth's oceans, but the moon's gravity is stronger on the side of Earth facing the moon, and slightly weaker on the far side. That difference in pull helps stretch the oceans into broad tidal bulges. Distance creates the difference. A relatively small change in distance across the width of Earth matters, because gravity fades so quickly as space opens up. The sun also raises tides, despite being much farther away because its mass is so enormous. Yet the moon has the stronger tidal effect on Earth, because it is so much closer. Again, mass matters, but distance matters enormously. A nearby smaller object can sometimes have a greater local effect than a distant giant. This principle reaches far beyond our solar system. A star can hold planets in orbit for billions of years. A cluster of stars can be held together by their combined gravity. A galaxy can gather hundreds of billions of stars into one immense rotating system. And yet galaxies remain vast. The stars within them are separated by distances so large that most of space is quiet, dark, and almost entirely empty. Gravity binds the galaxy together, but distance softens the pull enough to leave room for immense cosmic spaces. The universe is connected, but it is not crowded. Gravity reaches everywhere, but it does not reach everywhere with equal strength. That is the quiet wisdom of the inverse square law. A little farther away does not mean a little weaker. It can mean much weaker. Double the distance, 1/4 of the pull. Triple the distance, 1/9 of the pull. This simple pattern explains why the pull of a mountain does not overwhelm you, even though mountains contain enormous masses of rock. It explains why Earth dominates nearby objects. It explains why the moon remains bound to Earth without crashing into it. It explains why the sun can guide every planet while distant worlds move slowly through long, cold years. And it explains why, in the deep universe, gravity can be both weak and patient. A faint pull, given enough time, can still change everything. It can draw clouds of gas inward. It can gather dust into planets. It can pull stars into galaxies. It can slowly reshape orbits over millions or billions of years. Gravity does not need to hurry. It works through distance. It works through time. It whispers across empty space. And even when the whisper becomes faint, it never becomes nothing. The Earth still pulls on the moon. The sun still pulls on distant Neptune. Distant galaxies still pull faintly upon one another. Every object sends its quiet invitation outward. Come closer. Curve a little. Stay connected. And distance answers by softening that invitation, spreading it wider, making it fainter, but never fully silencing it. The moon is Earth's nearest large companion. Night after night, it rises above rooftops, trees, quiet roads, and sleeping oceans. It changes shape across the month. It appears to follow us as we travel. It brightens the darkness without making a sound. But the moon is not merely hanging there. It is pulling on Earth, and Earth is pulling on the moon. This pull is mutual. It's the same universal relationship Newton described between every pair of objects with mass. Earth has far more mass than the moon, so Earth's pull holds the moon in its long curved orbit. But the moon is still enormous. It is a world of rock, wide enough to cover thousands of kilometers from one side to the other, and its gravity reaches us. It reaches the ground beneath your feet. It reaches mountains. It reaches the air. It reaches the oceans. Most of the time, the moon's pull on a single person is too small to feel. You do not wake in the night feeling gently drawn toward the window. The moon does not pull a cup from your table, lift a bicycle into the sky, or cause people to behave unusually at dinner parties. Human history manages that last part without celestial assistance. But the oceans are vast. They are fluid. They can move. And across the broad diameter of Earth, the moon's gravity is not exactly the same everywhere. This difference is the beginning of the tides. Imagine Earth as a soft sphere covered mostly in water. Now imagine the moon standing far away, but still close enough to reach out with its invisible gravitational pull. The side of Earth facing the moon is slightly closer to it. The moon pulls a little more strongly on the water there. On the far side of Earth, the moon's pull is slightly weaker. This difference is small, extremely small. If you looked at Earth from far away, the stretching would be subtle, almost impossible to notice. But oceans are patient. They respond. Water gathers into a broad swelling on the side of Earth facing the moon. This is one tidal bulge, and there is another broad swelling on the far side of Earth. The reason for the far side bulge is a little more subtle, but we can understand its feeling without becoming lost in technical details. Earth and the moon are not simply one object pulling another from a fixed position. They are a pair, moving together around a shared balance point. Earth is pulled more strongly toward the moon than the water on the far side is. In this shared motion, the far side water lags slightly behind, creating another broad rise in the ocean. So Earth is gently stretched along the line between itself and the moon. One watery bulge faces the moon. The other faces away. It is like a soft, water-covered sphere being held very gently from opposite ends. Not squeezed, not shaken, stretched, slowly, quietly, continuously. And because Earth turns beneath these two broad ocean bulges, coastlines move through them. This is what we experience as tides. As a coastline turns toward one of the bulges, the sea rises. High tide arrives. Hours later, as the coastline turns away from the bulge and passes through a region with less raised water, the sea falls. Low tide arrives. Then Earth continues rotating. Another bulge comes around. The water rises again. This is why many coastlines experience 2 high tides and 2 low tides in roughly a day. Not exactly every 12 hours according to the clock, because the moon is also moving in its orbit around Earth. Each day, the moon has shifted a little farther along its path. Earth must turn a little more before a particular coast faces the moon in the same way again. That is why tides follow a lunar rhythm rather than a perfectly neat human schedule. The ocean listens to the moon, and the moon is always moving. There is something deeply strange about this if you pause long enough to feel it. A rocky world, nearly 400,000 kilometers away, quietly changes the level of the sea outside a coastal town. It reaches across space. It pulls differently on different parts of Earth, and the result is visible on shore. A harbor fills, a beach widens, boats rise against their moorings. Wet sand glistens where waves stood only hours before. Sea creatures wait in pools left behind by retreating water. Then, slowly, almost as though the ocean has remembered something, the water returns. The tide comes in. It's not rushed because the moon gives an order. It comes because the Earth has turned into a new position inside a gravitational relationship that has existed for billions of years. The sea is participating in a cosmic conversation. The moon speaks with gravity. Earth answers with motion. The oceans make that answer visible. Of course, the moon is not alone in influencing the tides. The sun also pulls on Earth. And the sun is enormously more massive than the moon. Its gravity holds Earth in orbit. It guides the whole solar system. It reaches far beyond our planet, into the cold distance where comets and icy worlds travel. So you might expect the sun to create much stronger tides than the moon. But tides are not caused only by the total strength of gravity. They are caused by differences in gravity across Earth's diameter. And this is where distance becomes important again. The sun is vastly more massive than the moon, but it is also vastly farther away. The moon, smaller but much closer, produces the stronger tidal, stretching effect on Earth. Still, the sun's effect is large enough to matter. And when the sun, Earth, and moon line up, the two influences combine. This happens during a new moon, when the moon lies roughly between Earth and the sun. It also happens during a full moon, when Earth lies roughly between the sun and moon. In both cases, the gravitational stretching from the sun and moon acts along nearly the same line. The ocean responds with more extreme tides. Higher high tides, lower low tides. These are called spring tides. The name has nothing to do with the season of spring, flowers, or birds, deciding that dawn begins too early. Spring here means a rising or leaping of water. Spring tides are the ocean's larger breaths. The sea reaches farther up the shore, then retreats farther away. At other times during the first quarter and third quarter phases of the moon, the sun and moon pull from directions that are closer to a right angle. The moon may be high in one part of the sky, while the sun's tidal pull stretches Earth from another direction. Their effects partly soften each other. The difference between high and low tide becomes smaller. These are called neaptides. The ocean still rises and falls. It still listens, but its rhythm is gentler. So the changing face of the moon is not only something to observe in the sky, it is also connected to the changing edge of the sea. A full moon may arrive, and the shoreline answers with stronger tides. A quarter moon appears, and the water's range becomes more restrained. Sky and ocean are joined by a force no one can see. This connection is older than every coastline, every ship, every lighthouse, every human story told beside the water. The moon has been drawing Earth's oceans into this slow rhythm for billions of years, and the oceans have been pulling back. The relationship is mutual. Just as Earth pulls on the moon pulls on Earth. Just as the moon shapes the tides gradually shape the moon's orbit. This happens very slowly, so slowly that no human life could feel the change unfolding. But over immense stretches of time, the tides act like a subtle brake on Earth's rotation. Earth turns a little more slowly than it once did. At the same time, the moon is gradually moving farther away. Not dramatically, not by enough to trouble tonight's moonlight, but the relationship evolves. Gravity does not simply create a fixed arrangement and walk away. It continues to work. It transfers motion. It changes paths. It reshapes systems over millions and billions of years. The Earth-Moon relationship is not a still picture. It is a long dance. The moon circles Earth. Earth turns beneath the moon. The oceans rise and fall. The tides tug gently at coasts, rocks, bays, estuaries, and islands. And slowly, almost invisibly, the dance changes both partners. This is one reason gravity is so much more than a story about objects falling down. Gravity can move oceans. It can shape the rhythm of shorelines. It can sculpt coastlines over time. It can lift and lower water with a force gentle enough to feel calm, yet large enough to move more water than any human machine could ever hope to command. Stand beside the sea at low tide, and the beach can feel enormous. Rocks appear. Seaweed lies across the sand. Small channels cut through the ground as water returns toward the open sea. Then come back later. The water has risen. The landscape has changed. The dry sand is gone. The rocks are underwater. The shore has been rewritten without noise, without urgency, by the combined movement of Earth, Moon, Sun, and water. We sometimes speak of the tide as if it is simply coming in or going out. But it is doing something grander. It is responding to the geometry of the solar system. It is revealing the shape of a gravitational relationship. The sea does not need to know Newton's equation. The water follows it anyway. Every drop participates. Every wave rises within a world pulled by the moon. Every high tide is a reminder that gravity is not confined to laboratories, textbooks, or the distant paths of planets. It is here at the coast. It is here in the harbor. It is here in the slow filling of an inlet under a darkening sky. Imagine Earth from far away. A blue sphere turning in sunlight. White clouds wandering above it. A small gray moon traveling nearby. Between them, no rope can be seen. No beam of light. No physical bridge. Yet Earth is slightly stretched by the moon's pull. Two broad ocean bulges travel with the Earth-Moon relationship, while the spinning planet carries every coastline through the changing water. It is delicate. It is immense. It is slow enough to soothe the mind. The moon pulls. The ocean answers. The shore waits. And twice each day, in many places around the world, the sea quietly shows us that even the vastness of space cannot prevent two worlds from touching each other through gravity. The solar system is not a collection of worlds sitting still in space. Nothing is simply hanging there. Earth is moving. Mars is moving. Jupiter is moving. The moon is moving around Earth, while Earth and the moon move together around the sun. Comets arrive from the cold outer darkness, sweep inward towards sunlight, and then disappear again for years, centuries, or far longer. Even the sun is moving, carrying the whole solar system on a great journey through the Milky Way. From far away, it might look almost peaceful. A bright star at the center. Planets tracing orderly paths around it. Small moons turning around their planets. Distant worlds moving slowly beyond Neptune. But this calmness is not stillness. It is motion held in shape by gravity. The sun is the great center of the solar system because it contains almost all of its mass. It is so massive that its gravitational pull reaches outward across billions of kilometers of space. Earth feels that pull. So does Mercury. So does Neptune. So do countless asteroids, wandering comets, icy dwarf planets, and small fragments of rock left over from the solar system's early days. The sun is continually inviting them inward, and each object is continually moving sideways. This is the beginning of every orbit. Without gravity, Earth would not travel in a curved path around the sun. It would move in a straight line through space, carrying oceans, clouds, cities, forests, and every living thing with it. A straight line is what motion prefers when nothing interferes. But the sun interferes. Not suddenly. Not harshly. It pulls Earth inward at every moment. Earth continues moving forward. The sun continuously bends that forward motion. The result is an orbit. Earth falls toward the sun, but it is moving sideways so quickly that it keeps missing. It misses the sun every moment of every day. And 1 year later, after traveling all the way around, it arrives once again near the place where it began. This is the pattern that holds the solar system together. Every planet is falling toward the sun. Every planet is also moving sideways. Gravity and motion create a path. A planet neither flies away nor crashes inward. It dances. Imagine a vast, silent dance floor, so large that light itself takes hours to cross from one side of the planetary region to the other. At the center stands the sun, not as a conductor waving a baton, not as a ruler giving orders, but as the great source of a quiet gravitational rhythm. Around it, every planet follows its own path. Mercury moves close to the sun, fast and bright, completing its orbit in only 88 Earth days. Venus follows farther out, hidden beneath its thick clouds. Earth travels in its familiar yearly path. Mars moves beyond us, red and distant. Then come the giant planets. Jupiter, enormous and striped with storms, carries a whole small system of moons around itself as it circles the sun. Saturn moves more slowly, surrounded by its wide pale rings. Uranus rolls along its orbit in a strange tilted way. Neptune travels at the outer edge of the major planets in cold blue darkness, taking more than 160 Earth years to complete one trip around the sun. They are all following the same fundamental law, but each has its own tempo, its own distance, its own speed, its own orbit. This is where another beautiful detail appears. The orbits of planets are not perfect circles. They are ellipses. An ellipse is like a circle that has been gently stretched, not wildly stretched in most cases. Earth's orbit is very close to circular, but it is not a perfect circle. During one part of the year, Earth is a little closer to the sun. During another, it is a little farther away. Other worlds travel in more noticeably stretched paths. Mars has a somewhat more oval orbit than Earth. Some comets follow extremely long ellipses. They spend most of their existence far from the sun, moving slowly through frozen darkness, then plunge inward, racing past the sun before turning outward again. Their paths can take decades, centuries, or thousands of years to complete. The solar system is not built from perfect circles drawn with a cosmic compass. It is built from moving bodies, shaped by gravity, carrying the history of their formation in the curves of their paths. And those paths change speed. A planet does not move around the sun at one unchanging pace. When it comes closer to the sun, gravity pulls more strongly. The planet speeds up. When it moves farther away, the sun's pull becomes weaker. The planet slows down. This is why a planet sweeps through the closest part of its orbit more quickly than the most distant part. It is like a dancer passing close to the center of a dance floor, moving quickly through the strongest part of the rhythm, then drifting outward into a wider, slower curve. Mercury, close to the Sun, moves astonishingly fast. It travels around the Sun at a speed far greater than Earth's. Earth moves more slowly than Mercury, but still faster than Mars. Jupiter, much farther out, takes almost 12 years to complete one orbit. Neptune, distant and dim, moves more slowly still. The farther a planet is from the Sun, the longer its year tends to be. Distance softens gravity. Gravity shapes speed. Speed shapes the orbit. And together, these relationships create the long calendar of the solar system. A on Earth comes from Earth turning on its axis. A year comes from Earth orbiting the Sun. A year on Mercury is brief. A year on Neptune lasts so long that a person born there, if such a person somehow existed, and had a very patient approach to birthdays, would wait more than a century and a half for their first one. Newton's law made this whole moving arrangement understandable. Before Newton, astronomers had already observed that planets followed regular paths. Johannes Kepler had described those paths with remarkable accuracy. He showed that planets move in ellipses, and that their speed changes as their distance from the Sun changes. Newton explained why. The same gravitational law that pulls an apple toward Earth reaches across the solar system. The Sun pulls the planets. The planets pull the Sun. The planets pull one another. The moons pull their planets. The asteroids pull faintly on nearby objects. Every body with mass participates in the same endless exchange. The Sun moves too. Because Jupiter is so massive, it pulls the Sun slightly. Saturn does as well. Earth, Venus, and the other planets all contribute their own tiny pull. The Sun and planets do not revolve around a perfectly fixed center inside the Sun. They move around a shared center of mass, a balance point that shifts as the planets continue their journeys. This does not make the solar system chaotic in the everyday sense. It makes it alive with relationships. A moving system, a slow gravitational dance, and it is more delicate than it first appears. Jupiter, for example, is the largest planet in the solar system. Its gravity is powerful enough to influence the paths of many asteroids. Between Mars and Jupiter lies the asteroid belt, a broad region containing countless rocky objects. Long ago, material in this region may have had the potential to form another planet, but Jupiter's enormous gravitational influence kept disturbing the orbits of the growing pieces. Instead of calmly gathering into one world, much of the material remained scattered. Jupiter is not merely a giant planet traveling alone. It is an organizer, a disruptor, a gravitational presence that has helped shape the solar system around it. Some asteroids travel in special patterns connected to Jupiter. They move in regions where Jupiter's pull and the Sun's pull create relatively stable arrangements. Other objects are nudged into new paths over long periods of time. Some are sent inward. Some are pushed outward. Some collide. Some are captured. The solar system has rules, but it is not frozen. It is orderly, but not motionless. Comets reveal this especially well. A comet may spend most of its life far beyond the known planets, in a region of deep cold where sunlight is weak, and the Sun appears only as an unusually bright star. Then gravity draws it inward. As it approaches the Sun, it gains speed. Frozen material on its surface begins to warm. Gas and dust escape, forming a glowing cloud around the comet and a long tail pointing away from the Sun. For a brief time, it becomes visible from Earth. People look up. They tell stories. They make predictions. They sometimes worry that the sky is sending a message, which is understandable when a glowing object with a tail appears unexpectedly above your village. Then the comet swings around the Sun and travels outward again. Gravity has bent its path. The comet has not chosen to visit. It is following a curve written by mass, motion, and distance. Some comets return often enough for humans to recognize them. Halley's Comet, for example, returns roughly every 75 years. It has passed Earth many times during recorded history. It appeared before the invention of electricity, before airplanes, before modern cities. It will return again, following the same broad gravitational path that has guided it for ages. Other comets may take thousands of years to come back. Their orbits are like long, slow breaths. Inward, outward, darkness, light, return. Beyond Neptune lie dwarf planets and countless icy bodies. Pluto is one of the most famous. It travels in an orbit that is more stretched and more tilted than the orbits of the major planets. At certain times, Pluto comes closer to the Sun than Neptune does. Yet, the two worlds do not collide. Their motion is arranged in a stable gravitational rhythm. They are linked by a pattern in which their positions repeat in a way that keeps them safely apart. This is another lesson of the solar system. Gravity does not only pull objects together, it can create stable patterns that prevent close encounters. It can organize motion into rhythms that last for millions or billions of years. It can make a system feel almost musical. Some worlds move quickly through short phrases. Others take long, slow turns. Together, they create a cosmic arrangement too vast to hear, but precise enough to calculate. And calculated, Newton's followers did. One of the great successes of Newtonian physics was its ability to predict where planets would be. If you knew the masses, positions, and motions of the major objects, Newton's laws allowed you to calculate their future paths. The calculations were difficult. They demanded patience, careful observation, and generations of mathematicians willing to spend large parts of their lives following planets that did not know they were being studied. But the predictions worked. Astronomers could forecast eclipses. They could track comets. They could calculate the positions of planets. They could notice when a planet's path was being disturbed by the gravity of another unseen object. This led to one of the most remarkable predictions in scientific history. In the 19th century, astronomers noticed that Uranus did not move exactly as expected. Its orbit had small irregularities. Something seemed to be tugging on it. Rather than dismissing the discrepancy, scientists wondered whether another planet might exist farther out, unseen in the darkness. Using Newton's gravitational law, mathematicians calculated where that unknown planet should be. Then astronomers looked. And there it was. Neptune. A world discovered not by accident, not by a ship arriving at a new shore, but by following the faint irregularities in another planet's motion. Gravity had revealed something invisible. This was a triumph not only for Newton's equation, but for a larger belief. The universe could be understood. Not completely, not easily, but through observation, thought, and careful calculation, hidden worlds could leave traces in the movement of visible ones. The solar system became a kind of clock, though not a rigid one. Its parts moved. They influenced one another. They shifted slowly over time, but they did so according to laws reliable enough to predict. Newton's universe was not a lifeless machine. It was more graceful than that. It was a moving architecture, a structure made from motion itself. The sun does not need walls to hold the planets. Gravity creates the structure. The planets do not need tracks. Their own momentum, curved by gravity, creates their paths. The moon does not need a chain attaching it to Earth. It falls around Earth in a stable rhythm. The entire solar system is held together by invisible relationships. And it has been dancing for about 4.5 billion years. Earth has completed billions of journeys around the sun. The moon has circled Earth countless times. Jupiter has traveled around the sun hundreds of millions of times. Neptune has completed only a few dozen orbits since the solar system formed, because its year is so long. Still, the dance continues. The paths are not perfectly unchanging. Over immense spans of time, gravitational nudges accumulate. Orbits shift gradually. Moons move outward or inward. Asteroids are disturbed. Comets are redirected. But the system endures, not because it is still, because its motion is balanced. So when you imagine the solar system, do not picture planets pinned in place around a bright central lamp. Picture movement. Picture Earth falling around the sun. Picture the moon falling around Earth. Picture Jupiter carrying its own family of moons while all of them fall together around the sun. Picture distant Neptune moving through darkness, traveling on a path so wide that its year lasts longer than a human lifetime. Picture comets arriving from the edge of the solar system, briefly glowing, then returning to the cold. And beneath every path, every curve, every returning season, imagine the same quiet rule at work. Mass pulls. Distance weakens the pull. Motion turns falling into orbit. The solar system is not a static clock. It is a dance floor without walls. The sun holds the rhythm. The planets answer in their own time. And gravity, silent and patient, keeps the entire dance from flying apart. Long before humans could leave Earth, we learned to predict the sky. We learned that eclipses were not warnings or accidents. They were alignments. The moon passing between Earth and the sun, or Earth passing between the sun and the moon. A precise arrangement of moving worlds. We learned that comets could return, not necessarily on a schedule convenient for human memory, but on paths that could be calculated. A comet might vanish into the deep darkness for decades, then return exactly where gravity said it should return. And this was one of the quiet triumphs of understanding gravity. The heavens stopped being only mysterious. They became predictable, not completely controlled, not owned, but readable. Newton's equation helped make this possible. It told scientists that the moon, the planets, and comets were not wandering through space at random. They were following paths shaped by mass, distance, and motion. If you could observe a body carefully enough, measure its position, understand its speed, and account for the gravitational pulls around it, you could look ahead. You could predict where it would be tomorrow, next year, a century from now. This did not make the universe less beautiful. It made it more beautiful, because the sky was not chaotic. It had rhythm, a hidden order, a patient geometry, and eventually, humans learned not only to predict objects moving through the sky, we learned to place objects there ourselves. These objects are satellites. A satellite is simply an object that travels around another object because of gravity. The moon is Earth's natural satellite, but humans have built thousands of artificial satellites, each one placed into a carefully chosen orbit around Earth. Some watch the weather. Some carry television, radio, telephone, and internet signals. Some help ships cross oceans. Some guide airplanes through clouds and darkness. Some help emergency workers locate people who need help. Some look outward, beyond Earth, studying the sun, distant stars, galaxies, and the faint background glow left from the early universe. And some quietly help your phone tell you where you are. This is one of the strangest ordinary things about modern life. You stand on a street in an unfamiliar city. You take out a small object that fits in your hand. A map appears. A blue dot tells you where you are. Perhaps it tells you which direction to walk. Perhaps it warns you that the next train is late. Perhaps it helps a driver find a quiet road, a ship find a harbor, or a rescue team find someone lost in the night. All of this depends, in part, on objects falling around Earth. Satellites are not beyond gravity. They are not floating in a place where Earth's pull has ended. They are held in orbit by gravity, just like the moon, just like Earth around the sun. The difference is that satellites are much smaller, much closer, and placed into their paths by human hands and human machines. To understand this, imagine once again that you are standing on an impossibly high mountain. You hold a ball, throw it gently, and it falls nearby. Throw it harder, and it travels farther before reaching the ground. Throw it faster still, and the curve of Earth begins to matter. The ball falls, but the ground curves away beneath it. At the right speed, the ball keeps falling around Earth. It becomes a satellite. This is the basic idea behind every orbit. A rocket does not carry a satellite upward merely to get it away from Earth. It carries the satellite upward through the thick lower atmosphere, where air would slow it down. Then, crucially, it gives the satellite enormous sideways speed. That sideways speed is everything. Too little speed, and the satellite falls back toward Earth. Too much speed, and it may drift into a wider path or escape Earth's pull entirely. But at just the right speed, at just the right height, gravity bends the satellite's forward motion into a stable orbit. The satellite continues falling. Earth continues curving away, and the satellite keeps missing the ground. Again, and again, and again. A satellite is like a note placed perfectly into a long, circular musical phrase. If the note is too slow, it falls out of rhythm and returns to Earth. If it is too fast, it drifts away from the melody. But at the right speed, it continues circling, returning again and again to the same great pattern. Gravity provides the rhythm. Motion carries the note forward. Together, they make orbit. There are many kinds of orbits because different jobs require different paths. Some satellites travel relatively close to Earth. They move quickly. A satellite close to Earth can circle the planet in roughly an hour and a half. It rises over one part of the world, races across the sky, and soon disappears over the horizon. These lower satellites are useful for observing Earth in detail. They can study clouds, forests, ice sheets, ocean currents, fires, cities, and changing landscapes. Weather satellites help scientists watch storms forming over oceans. They follow hurricanes, track clouds, and measure patterns in the atmosphere. They do not control the weather, sadly. If they did, many people would begin submitting formal complaints about rainy weekends. But they help us see what is coming. They give warnings. They help communities prepare. They allow meteorologists to look down upon the turning atmosphere and understand its slow, restless movements. Other satellites travel much farther from Earth. At greater distances, gravity is weaker, and an orbit takes longer. Some satellites are placed so carefully that they circle Earth at the same rate Earth turns. From the ground, they appear to remain above nearly the same region of the planet. They seem almost still. They are not still, of course. They are traveling at great speed, tracing a vast circle around Earth. But they are moving in harmony with Earth's rotation. These satellites are especially useful for communication. A signal can travel upward from a station on Earth to the satellite, then return downward to another place far away. A television broadcast can cross continents. A phone call can reach across oceans. A message can travel from a remote region to the rest of the world. All because a carefully placed machine is falling around Earth in the right rhythm. There are also scientific satellites. Some turn their instruments toward Earth, others turn away from it. They look beyond the atmosphere, where there are no clouds, no weather, and no air to blur the view. From orbit, telescopes can observe parts of the universe that are difficult or impossible to study from the ground. They can listen for faint signals. They can measure light from distant stars. They can watch the sun. They can search for planets around other stars. They can study galaxies so distant that their light began traveling toward us before Earth existed in its present form. These satellites are quiet observers. They do not go to space to conquer it. They go to listen, to look, to collect small pieces of information from a universe too large to hold in any one human mind. Then there's the network of navigation satellites. This network is often called GPS, short for Global Positioning System. Though similar satellite navigation systems are also operated by other parts of the world. These satellites orbit high above Earth, each carrying extraordinarily precise clocks that continuously send out signals. Your phone, your car, a ship at sea, or an airplane in flight receive signals from several satellites at once. By comparing the tiny differences in the arrival times of these signals, a receiver can work out where it is. Not by magic, not because the phone sees a map from above, but because it listens to time. A signal from one satellite takes a certain amount of time to arrive. A signal from another takes slightly longer or shorter. With enough signals, the device can calculate its position on Earth. It can locate itself. It can tell you where you stand. This requires extraordinary precision. Light moves incredibly fast, so even a very small error in time can create a large error in location. A clock that is wrong by a tiny fraction of a second can make a navigation system think you are somewhere you are not. Perhaps several streets away. Perhaps in a river. Perhaps, if technology is feeling especially philosophical, in the middle of a field you have never visited. So the clocks aboard navigation satellites must be kept remarkably accurate. And here, gravity becomes important again, in an unexpected way. Time itself passes slightly differently in different gravitational conditions. A clock farther from Earth, where gravity is weaker, ticks at a subtly different rate from a clock on the ground. The effect is tiny. You would never feel it. You would not wake up in orbit thinking the morning had become strangely philosophical. But the effect is real, and precise enough that satellite systems must account for it. Without these corrections, GPS positions would gradually drift and become useless. This is one of the beautiful surprises hidden inside ordinary navigation. When a phone tells you where you are, it depends on satellites in orbit. Those satellites depend on Newton's gravity to remain in their paths. And their clocks must also account for the deeper understanding of gravity developed by Einstein centuries later. A person asking for directions in a quiet, unfamiliar neighborhood is, without realizing it, relying on some of the greatest ideas in the history of science. Gravity is there, silent, precise, working in the background. Satellites also help us understand Earth as one connected world. They watch ice melt near the poles. They measure the height of the sea. They observe changes in forests and deserts. They follow smoke from large fires. They track the movement of clouds and water vapor around the planet. From the ground, it is easy to feel that weather is local. A rainy day belongs to your town. A dry summer belongs to your region. A storm belongs to one coastline. But from orbit, the atmosphere appears as one moving system, wrapping around the entire planet. Clouds cross borders without noticing them. Oceans carry warmth from one hemisphere to another. Winds connect distant places. Gravity holds all of it close to Earth. The air remains gathered around our world because Earth pulls it inward. The oceans remain here because Earth pulls them inward. And satellites, moving far above both air and sea, are held in their own paths by that same pull. Understanding gravity also makes space travel possible in a more subtle way. To travel from Earth to the Moon, or from Earth to another planet, a spacecraft does not simply point itself in a direction and push forward as hard as possible. It must work with gravity. It must enter the right orbit. It must leave at the right moment. It must travel along a path shaped by Earth's pull, the Sun's pull, and eventually the pull of its destination. A spacecraft going to Mars, for example, follows a wide, graceful curve around the Sun. It does not travel like an arrow fired directly at Mars. It moves along a route that allows it to meet Mars, where Mars will be later. This requires patience and calculation, and a deep respect for the fact that planets are never waiting in one place. They are always moving. Gravity is not merely an obstacle to overcome. It is part of the route. A spacecraft can use the gravity of a planet to change direction or gain speed. It can sweep past a world and borrow a little of that world's orbital motion. This is called a gravitational assist. It is a delicate maneuver. A spacecraft approaches a planet. The planet pulls it. The spacecraft's path bends, and it leaves with a new speed or direction. No giant engine is required during that part of the journey. Gravity does the steering. In this way, human technology has learned something important. We do not need to defeat gravity. We can learn its patterns. We can calculate its rhythms. We can place a satellite into a long, stable fall. We can send a spacecraft across the solar system by following curved paths that gravity already makes possible. We can predict eclipses. We can anticipate comet returns. We can guide airplanes and ships. We can study storms. We can find our way home, all through an invisible force that once seemed as ordinary as a dropped stone. And perhaps this is the quiet lesson of gravity in human life. The greatest technologies are not always built by forcing nature to obey us. Sometimes they are built by noticing what nature has been doing all along. Gravity pulls. Objects move. Paths curve. Orbits form. Human beings learn to listen to this pattern. Then carefully, we learn to join it. Above the clouds, thousands of satellites continue their calm journeys. Some race around Earth again and again. Some remain far away, keeping pace with the turning planet. Some watch storms. Some carry messages. Some listen to distant stars. Some help a traveler find a street, a pilot find a runway, or a rescue team find a person in need. They do not hover by escaping gravity. They remain aloft because gravity holds them in motion. Each one is a carefully calculated fall. Each one is a small object moving through darkness, held in a precise relationship with Earth. And beneath them, the planet turns. The oceans shift. The clouds wander. Cities glow at night. People sleep, travel, work, and look at maps on small bright screens. All while, gravity continues its oldest task, not making a sound, not asking to be noticed, simply keeping the moving world connected. For more than 2 centuries, Newton's law of gravity appeared almost perfect. It explained why apples fall, why the moon circles Earth, why Earth circles the sun, why tides rise and fall, why comets return, why planets move through the sky in paths that can be predicted years, centuries, even generations in advance. It gave sailors better maps of the heavens. It helped astronomers discover new worlds. It made satellites possible long before satellites existed. Newton's equation was not merely useful, it was astonishingly successful. And it still is. If you want to calculate the fall of a ball, Newton worked. If you want to launch a satellite, Newton works. If you want to predict the moon's orbit, guide a spacecraft through much of the solar system, understand the tides, or calculate the path of a comet, Newton works extraordinarily well. The equation remains one of humanity's most useful descriptions of nature. This is important to say clearly. Newton was not replaced because his theory was foolish. He was not proven wrong in the simple way an old rumor is proven wrong. His theory was too successful for that. Instead, scientists discovered that it had limits. It was like a beautifully accurate map that worked almost everywhere, until someone began traveling into the most remote and difficult terrain. And there, in the details, tiny mismatches began to appear. At first, these mismatches were almost invisible. The solar system seemed to move exactly as Newton had described. Planets followed their paths. The moon returned. Comets came and went. The clockwork of the heavens kept time with remarkable reliability. But one planet was slightly troublesome: Mercury. Mercury is the smallest major planet in the solar system. It travels very close to the Sun. Its year is short. It races around the Sun faster than any other planet, completing one orbit in only 88 Earth days. And because Mercury travels so near the Sun, it lives in a place where gravity is stronger and the conditions are more extreme. Its orbit is an ellipse, like the orbit of every planet. But the ellipse does not stay perfectly fixed in space. Over time, it slowly turns. Imagine drawing an oval on a table. Then, after every trip around the Sun, imagine that oval shifting by a tiny amount, like the hand of a clock moving forward almost too slowly to see. This slow turning is called precession. Newton's gravity could explain most of Mercury's precession. The pull of the other planets, especially Venus and Jupiter, slightly disturbed Mercury's orbit. Their gravity added small nudges, changing the path little by little. Newton's calculations accounted for nearly all of it, but not all. There was a small leftover amount, a stubborn discrepancy. Mercury's orbit turned just a little more than Newton's theory predicted. The difference was tiny. So tiny that it would never matter to a person standing outside on a sunny afternoon. It would not cause Mercury to fall into the Sun. It would not make the planet visibly wobble across the sky. But in science, a small unexplained detail can become very important. Nature does not owe us perfect agreement merely because we like an equation. If the universe gives a different answer, even by a whisper, then the whisper deserves attention. For decades, scientists wondered what might be causing Mercury's strange extra motion. Perhaps there was an undiscovered planet closer to the Sun. Maybe a hidden world, too dim to see, was tugging on Mercury from the shadows. Astronomers searched. They looked near the blazing edge of the Sun during eclipses, hoping to glimpse an unseen planet. They gave this imagined world a name: Vulcan. Not the fictional world that would later become famous in stories, but a proposed planet of the 19th century. Vulcan was supposed to exist inside Mercury's orbit, close to the Sun, quietly disturbing Mercury with its gravitational pull. It was a reasonable idea. Newton's law had helped predict Neptune by noticing irregularities in Uranus' orbit. Perhaps the same method would reveal another hidden planet. But Vulcan was never found. The mismatch remained. Mercury continued to move with a quiet, tiny disobedience. And in time, the problem became a clue. Gravity, it seemed, might be more subtle than Newton had imagined. Not wrong in ordinary conditions. Not broken near Earth. Not useless for planets and moons. But incomplete near enormous mass, extreme speed, and the highest levels of precision. Then came Albert Einstein. Einstein entered this story in the early 20th century, more than 200 years after Newton published his great law of universal gravitation. Like Newton, Einstein was interested in questions that seemed simple until you looked at them closely. What is light? What is time? What is motion? And what, exactly, is gravity? Newton had described gravity as a force. Every mass pulls on every other mass across space. It was an elegant description, and it worked. But Newton himself had been uncomfortable with one aspect of it. How did gravity reach across empty space? How could the Sun pull on Earth from so far away without a visible connection between them? Newton could calculate the pull with extraordinary accuracy, but he did not claim to know the deeper mechanism underneath it. Einstein approached the problem differently. He asked us to imagine that gravity is not only a force acting through space. What if gravity is part of the shape of space itself? And what if time too is involved? This is where the story becomes strange in a new and beautiful way. Space and time are not separate things, according to Einstein. They are woven together into one larger fabric. Space-time. It is not a fabric in the ordinary sense. It does not have threads. You cannot fold it into a drawer. It does not need ironing, which is fortunate, because the universe is very large and humanity has not yet mastered the smaller versions of that task. But the fabric image can help us feel the idea. Imagine a vast, smooth surface. Place a heavy object in the middle. The surface bends around it. Now roll a smaller object nearby. The smaller object follows a curved path, not because the heavy object has reached out with an invisible rope, but because the space around it has been shaped. This is only an analogy. Real space-time is not a flat sheet, and gravity does not require an outside direction called down. But the image points toward Einstein's central thought. Mass changes the geometry of space-time, and curved space-time guides motion. Earth travels around the sun because the sun changes the shape of space-time around it. The moon travels around Earth because Earth changes the shape of space-time around it. An apple falls because it follows the curved structure of space-time near Earth. In Newton's picture, gravity pulls objects inward. In Einstein's picture, mass and energy shape space-time, and objects move along the curves that shape creates. The result for ordinary life is almost exactly the same. Drop a cup. It falls. The moon orbits Earth. Earth orbits the sun. Newton and Einstein agree remarkably well in familiar conditions. That is why Newton remains so useful. His theory is simpler to calculate, and for most situations, it gives answers accurate enough to trust completely. A builder designing a bridge does not need general relativity. A person calculating the path of a thrown ball does not need curved spacetime. A spacecraft engineer often begins with Newton. Even many journeys through the solar system can be planned with Newton's laws to a remarkable degree of accuracy. Newton's gravity is not a failed theory. It is an approximation. A very good one. Think of it as a map of a country. The map shows roads, rivers, towns, mountains, and coastlines. It tells you where you are going. It helps you travel. It is detailed enough for almost every journey you will ever take. Then imagine that, in the deepest mountains, the terrain becomes strange. The ground curves in ways the map does not fully capture. The distances shift slightly. The path that looks straight on paper turns out to bend in the real landscape. The map was not useless. It was not a lie. It was simply not detailed enough for the most extreme terrain. Einstein revealed that, near great masses, at great speeds, and under the finest measurements, the landscape of reality itself bends and curves. Mercury was one of the first places where this deeper map proved its value. Einstein's theory of general relativity predicted that Mercury's orbit should shift by exactly the extra amount Newton's theory could not explain. Not approximately, not vaguely. The calculation matched a mysterious leftover motion. Mercury's small disobedience was no longer disobedience. It was evidence, a message from nature. Gravity was not merely a pull between masses. It was also the shape of spacetime. This was one of the great moments in science. A tiny mismatch in the orbit of a small planet helped reveal a new picture of the universe. And the new picture led to even stranger discoveries. Einstein's gravity predicted that light itself could bend. This sounds impossible at first. Light has no rest mass in the ordinary sense. It does not travel like a thrown ball. It moves at the fastest speed nature allows. But if spacetime is curved near a massive object, then light follows that curvature too. A beam of starlight passing close to the sun should appear slightly bent. During a solar eclipse in 1919, astronomers measured the positions of stars near the darkened sun. The observations supported Einstein's prediction. The news traveled around the world. Einstein became famous, and gravity became stranger than ever. It could bend light. It could slow time. It could curve the path of a planet. It could make clocks tick at slightly different rates depending on where they were and how they moved. This is not only an abstract idea. It matters in the technology we use today. Navigation satellites high above Earth experience gravity differently from clocks on the ground. Their clocks tick at a subtly different rate. Systems such as GPS must correct for this effect to remain accurate. Without Einstein's corrections, your location on a map would slowly drift. The blue dot on your phone would become less certain each day. It might place you on the wrong street, then the wrong neighborhood, then perhaps somewhere in a lake, calmly insisting that you had taken an unusual shortcut. Newton gets us extraordinarily far. Einstein helps us finish the journey. But even Einstein's theory has limits. General relativity is magnificent at explaining gravity on large scales. It describes planets, stars, black holes, galaxies, and the expanding universe. It predicts gravitational waves, faint ripples in spacetime, produced by violent cosmic events. These waves were eventually detected, more than a century after Einstein predicted them. It explains why light bends around massive objects. It helps us understand black holes, places where gravity becomes so intense that the shape of spacetime is bent beyond anything we encounter in daily life. And yet, when scientists try to combine Einstein's gravity with quantum mechanics, the theory of the smallest things, another problem appears. The two great descriptions of nature do not fit together easily. Quantum mechanics describes a world of probabilities, uncertainty, particles, and fields. General relativity describes a smooth, continuous spacetime shaped by mass and energy. Both theories work astonishingly well in their own domains. But in the most extreme places, deep inside black holes, or during the earliest moments of the universe, we may need a deeper theory still. A theory of quantum gravity. No one has fully found it yet. This is not a failure of science. It is the shape of science. Each great theory reveals a part of reality with new clarity. Then, at its edge, new questions appear. Newton opened the door. Einstein walked farther through it. And beyond Einstein, the hallway continues into darkness. That darkness is not empty. It is full of unanswered questions. What is gravity at the quantum level? What happens at the very center of a black hole? Was spacetime itself once different in the earliest universe? Is gravity truly fundamental, or does it emerge from something deeper? We do not yet know. And there is something comforting about that. The greatest theories do not end curiosity. They deepen it. Newton looked at falling things and saw the moon. He looked at the moon and saw a universal law. Einstein looked at that law and saw curved spacetime. Future thinkers may look at curved spacetime and see another layer beneath it. Perhaps they will find a new map. Perhaps they will discover that space, time, matter, and gravity are parts of an even deeper unity. For now, Newton's equation remains with us. Simple, powerful, reliable. It still describes the pull that holds you to Earth. It still guides satellites. It still predicts the moon's path. It still helps spacecraft travel through the solar system. It still explains the patient architecture of orbits. Newton did not give us the final word on gravity, but he gave us the first great sentence. And that sentence changed how humanity saw the universe. The world was no longer divided between Earth and sky. The apple and the moon belonged to the same story. The ocean tide and the distant planet belonged to the same story. The falling stone and the orbiting spacecraft belonged to the same story. Then Einstein showed us that the story had another chapter. Gravity was not only a quiet pull. It was the curvature of the stage on which all motion unfolds. And perhaps that is the most peaceful lesson of all. Understanding does not remove mystery. It gives mystery a clearer outline. It lets us see how much farther there is to go. Newton's map remains beautiful. Einstein's map reaches deeper. And beyond both of them, the universe continues quietly bending, moving, falling, orbiting, and waiting for the next question. The universe is quiet tonight. Not empty. Not still. Quiet. Around you, gravity is working. The bed beneath you has mass. The room around you has mass. The walls, the floor, the roof, the furniture, the books, the glass in the window, the water in a cup somewhere nearby, all of it is pulling on all of it. Very gently. The bed pulls on you. You pull on the bed. The walls pull on you. You pull on the walls. Even a book resting on a shelf is tugging, ever so slightly, on every other object in the room. These pulls are real. They are not poetic. They are not symbolic. They are part of the physical universe, but they are far too small to feel. Earth is simply much larger. Its mass is so immense, and you are so close to it, that Earth's gravity dominates the small neighborhood around you. The pull from your bed is there, but Earth speaks more loudly. The pull from the moon is there too. The pull from the sun, the pull from the distant stars. Everything reaches toward everything else. But not all invitations have the same strength. Earth holds you close. The moon gently stirs the oceans. The sun guides Earth through its long yearly path. The stars pull upon one another across the dark spaces between galaxies. And every object, however small, adds its own faint voice to the endless gravitational conversation. A grain of dust pulls on another grain of dust. A raindrop pulls on the leaf beneath it. A mountain pulls on the clouds drifting above it. A person pulls, imperceptibly, on the person sitting beside them. Gravity is never absent. It only becomes too quiet for us to notice. This is one of the strange comforts of the universe. Nothing is completely alone. Not in the physical sense. There may be vast distances, dark distances, distances so large that light needs millions of years to cross them. But gravity still reaches. It weakens. It spreads. It becomes unimaginably faint. Yet it does not simply stop. A distant galaxy pulls gently on our own galaxy. Our galaxy pulls gently back. Two stars separated by a great gulf of darkness still share a relationship. It may be a whisper, but it is a real whisper. The universe is not a collection of isolated islands scattered in a black sea. It is more like a dark ocean in which every island creates a gentle current. Each current reaches outward. Each one touches another shore. Some currents are powerful. A star gathers planets around it. A galaxy gathers billions of stars. A black hole bends the paths of light itself. Other currents are almost too weak to name. A pebble beside another pebble. A sleeping cat beside a chair. A cup resting quietly on a table. But the rule is the same. Mass pulls on mass. Distance softens the pull. And the universe becomes a vast web of quiet connection. Gravity is one reason anything exists in the forms we recognize. In the beginning, there were vast clouds of gas and dust drifting through space. Gravity gathered them. Not instantly. Not dramatically. Slowly. A faint attraction between particles brought some of them closer together. As more material collected, the pull grew stronger. More gas arrived. More dust arrived. The cloud began to turn, compress, warm, and change. Eventually, in some places, stars were born. Inside those stars, light began. Heat began. The long work of making heavier elements began. Then, around young stars, gravity gathered smaller pieces of dust and rock. Tiny fragments collided. Some stuck together. Others broke apart. Over immense spans of time, small bodies became larger ones. Dust became stones. Stones became worlds. Worlds became planets. Planets gathered moons. And the same quiet pull that formed them kept them moving through space in lasting patterns. Gravity did not build the universe like a carpenter building a house. It had no blueprint, no hands, no voice. It simply pulled. And over enough time, pulling became structure. Structure became stars. Stars became solar systems. Solar systems became part of galaxies. Galaxies gathered into larger groups, drifting through the darkness together. Gravity is patient enough to make order from scattered dust. Patient enough to turn a cloud into a star. Patient enough to keep a moon circling Earth for billions of years. Patient enough to shape a universe that can eventually produce oceans, trees, animals, music, questions, and someone lying quietly at night, listening to the story of a falling apple. And here you are, made from matter that has traveled a very long way. The atoms in your body were not all made on Earth. Many were formed in ancient stars. Some were scattered into space when stars ended their lives. Then they became part of new clouds, new worlds, new oceans, new living things. The calcium in your bones, the iron in your blood, the oxygen you breathe, the carbon in every cell. All of it follows the same laws that guide moons and planets. Your body is not outside the story of gravity. It belongs to it completely. Earth gathered the materials that formed it. Earth's gravity held oceans close enough for life to continue. It held an atmosphere around the planet. It kept rain returning to the ground. It helped shape the conditions in which forests could grow, rivers could flow, and living creatures could rest beneath the night sky. Gravity is not only the reason things fall, it is part of the reason there is a place for things to fall on. It gathered the world beneath you. It holds the air around you. It holds the moon nearby enough to brighten the night. It gives shape to the vast moving architecture of the cosmos. And it does this with no visible effort, no sound, no announcement. A planet turns. A moon circles. A tide rises. A leaf falls. A satellite moves through darkness. A distant star bends the path of light. Gravity is there, quietly making curves, quietly creating returns, quietly holding motion together. We began with Newton's simple discovery. The same rule that guides an apple toward Earth also guides the moon around it. The same relationship reaches from a room on Earth to the edge of the solar system. And the whole idea can be gathered one final time into a single calm sentence. The gravitational force between two objects depends on the mass of the first object, the mass of the second object, and the distance between them. More mass means more pull. More distance means less pull. That is Newton's equation. Not as a test, not as a puzzle, just as a compact story of connection. Two objects, two masses, a distance, an invisible pull. The equation does not tell us everything about gravity. Einstein showed us that the deeper story involves the shape of space and time, and future discoveries may show us something deeper still. But Newton's simple rule remains beautiful. It reminds us that the universe is not divided between the ordinary and the cosmic. The cup on a table, tide at a shore, the moon in the sky, the planet beneath your bed, the sun at the center of its wide family of worlds. They all belong to the same story. They all answer the same quiet call. Tonight, you do not need to calculate anything. You do not need to follow every orbit. You do not need to imagine every star, every galaxy, every distant current moving through the dark ocean of space. You can simply rest. The ground is beneath you. The room is around you. Earth is turning slowly. The moon is moving through its familiar path. The oceans are rising somewhere and falling somewhere else. Clouds are drifting. Satellites are circling. Planets are continuing their long, patient journeys around the sun, and gravity is holding the great moving pattern together. Not perfectly, not forever, in exactly the same form, but gently, faithfully, moment by moment. The bed pulls faintly upward toward you. You pull faintly downward toward it. Earth holds you both. The moon holds its distant conversation with the sea. The sun holds its distant conversation with Earth. And beyond the sky, beyond the stars, beyond everything the eye can see, every island in the dark creates its own small current. Every current reaches outward. Every shore is touched. So let the day become quieter now. Let the thoughts become lighter. Let the room remain where it is. Let Earth do what it has always done. Hold you close. And let the universe continue its endless, silent work. Pulling, turning, gathering, falling, orbiting, connecting everything to everything else. Quietly, through the dark.